Okay, so welcome everybody. Um, Thanks to the organizer and to SAGEX for inviting me to give this lecture. So just before we start, a few comments about how the lecture is organized. So first is, well, you see my face now, but I will keep the camera off during the lecture just to save some bandwidth. But I will be around even if you don't see me. And the other thing, if you have any questions, feel free to ask anytime. Feel free to interrupt me even during the lecture. Lucy kindly agreed to keep an eye on the chat or if you raise hands. And but you can also just speak up and just ask your questions directly. Okay, so I guess then we can start. So the topic of the lecture is differential equations and calculation of Feynman integrals. And well, I guess Feynman integrals is something you've all heard of because that is what, in some sense, the topic of SAGEX is all about, at least part of it. And, or rather, what SAGEX is about is scattering amplitudes. And I guess you all know why we care about them, because those are the objects that we want to compute in order to make predictions for collider experiments like the LHC. So I don't think that this is big surprise to any of you. I won't spend a lot of time on this slide. It's just to set the scene. And okay, just to tell you what is in the slide in case you're not too familiar with it. What you care about is making predictions for probabilities at LHC, for example, where you collide two protons to produce some final state X. And the way that works is, well, the protons are non-perturbative objects. So you have two incoming protons here and here. Now, of course, the protons are non-perturbative objects. We cannot compute with those states directly, but there's a way to split the calculation into pieces, one which involves what's called pattern distribution functions. If you don't know what they are, it's not so important. Those describe the internal structure of the proton. And then there's a quantity, which I denote here sigma hat, which describes the cross-section, or if you want, the probability to produce a state X when you collide quarks and gluons, so the fundamental constituents of the proton. And it's this sigma hat that is actually obtained from the scattering amplitude A, which is what we are all interested in, which is scattering amplitude. So this A, the scattering amplitude, is one of the fundamental ingredients that you need if you want to compute predictions for collider experiments. But also, as you probably know, nowadays the same techniques are being applied, for example, to gravitational waves. So, but as I'm a collider physicist, I'm mostly interested in the perspective of collider events. That's why I use as a motivation here LHC collisions. So I want to compute this A, this scattering amplitude, and I want to do it for external states that are quarks and gluons. Now, I guess you also know that quantum field theory is hard, and we just don't know how to do exact computations in quantum field theory, at least not in general. And the best we can do is perturbation theory. So perturbation theory, as I guess you know, and you assume that the theory has a small coupling constant, and you organize the calculation as an expansion in the small coupling constant. For example, if you think again about scattering, for example, if you think about 2-to-2 scattering, then, well, we know that the leading order term, or tree level, is, well, corresponds to all tree diagrams, but then the next term would involve one loop diagrams where now you have like this one closed loop in your graph. The next term would be two loop diagrams where you now have two closed loops, and so on and so forth. And the complexity grows very quickly with the number of loops in your graph, in the sense that one could say that tree-level calculations are nowadays, you could say, easy. In this, you could almost say it's like a solved problem. One-loop computations are not necessarily easy, but nowadays we know how to do that. We have efficient techniques, we have computer codes how to do that. And starting from two loops, that is where the frontier lies. And some of the other lectures by Ben and by Young, I guess they touch on the questions of how you can set up two-loop calculations, and also in particular, how can you kind of leverage some of the techniques that have made one-loop computations accessible, how you can leverage them to two. So that is the scene, that is the setting. So well, then, for now, let's assume that you just know how to write down your Feynman diagrams. Okay, so we have the Feynman diagrams. What you will need to do is you will need to compute your Feynman integral. So you will need to integrate over the momenta of these quanta that you exchange. Because you can easily convince yourself that if you have a tree-level diagram, all the momenta in your graph are fixed as soon as you fix the external edges. But if you have a loop diagram, there's one momentum per loop that you cannot fix. It's very easy to see. For example, if you have a one loop graph, there's the momentum of flowing in this loop here that you cannot fix from external, from the external momenta, from momentum conservation. It's like something that's running around in circles and you cannot fix it. And it's quantum mechanics, so you have to sum of all possible quantum numbers of all possible intermediate states that you cannot observe. So you have to sum of all of these momenta that flow in this loop. And so you have to integrate over them. So you will always have to compute these integrals as soon as you go beyond tree level. And so what the lecture is going to be about, the lecture will be about ways of tackling these loop computations, of tackling the computation of these integrals. I will not discuss how you would actually get the expression for the scattering amplitude, like the integrand. I will just discuss the computation of the integrals. So these integrals is what we call Feynman integrals. And well, the integrals that we will consider are as shown here on this slide. Some comments, I will only consider what is called scalar integrals. I will not discuss tensors. It's not a restriction because you, at least in principle, you can always reduce everything down to scalars if you do tensor reduction. It's something you probably know from your quantum field theory classes, something, for example, at one loop, it's often called Passerino-Weltman reduction. You can always, if you have integrals that have open Lorentz indices, say in the numerator, you can always get rid of them and write it in terms of scalars. And as soon as you restrict yourself to scalars, the most general integral that you can have at L loops looks as follows. So there's one integral per loop, so one loop momentum per loop. The space-time dimension I denoted by d. So for now, I just keep it generic. So d would be equal to 4. And then for every edge in my graph, I have to put a propagator, which is some momentum squared minus the mass squared of the particle flowing in the propagator. And I can also have some numerators. And by Lorentz invariance, they must then be dot products. And they must be polynomials, because my Feynman rules would only ever give me polynomials. And they can then be polynomials in dot products between two loop momenta, or between, oops, sorry for that, or between a loop momentum and an external momentum. The piece will always denote, for me, external momenta, while the case will be the loop momentum. And so my n, my numerator, will be a polynomial in these dot products. And I will assume that this polynomial is homogeneous. homogeneous in like the energy dimension. So if I have, for example, a term that has energy dimension 2, then all the terms should have energy dimension 2. I can always arrange for that. That's not a restriction. And in addition, something that may sound strange now here is that I will allow arbitrary powers for the propagators. So every propagator could be raised to some arbitrary power, integer power, negative or positive. Of course, your propagators would only have nu equals 1 when you look at your Feynman rules. But as we will see, it will be very convenient to allow arbitrary nus. So for now, that is the most general quantity I want to consider. I have kept everything arbitrary. I have some random collection of external momenta. They, however, satisfy momentum conservation. I have arbitrary powers for the propagators, and I allow arbitrary polynomials in the numerator, the only restriction being that they are Lorentz invariant and that they're homogeneous. So those are the integrals that I want to compute. So what do I know about them? Well, the first thing already is obvious is that these integrals must themselves be Lorentz invariant, because the integration measure is Lorentz invariant, the integration region is Lorentz invariant, it's the whole space, and the integrand is Lorentz invariant. So in the end, my integrals, as I defined them, will only depend on the dot products between the external momenta. So that's the first property that I can immediately say. So my integrals will be Lorentz invariant. It will only depend on the dot products between external momenta. Another property which one has to keep in mind is that these integrals very often diverge. So I have to make sense out of these divergent integrals if I want to get a number. There are two kinds of divergences, so I'm not going to say much about it because it's not so important for this lecture, but I guess you also know it, that you have, for example, UV divergences, which you remove by renormalization. But I also have in massless theories like Young-Mills, you have infrared divergences, which you cannot remove by renormalization. They will cancel against other contributions that you need to compute. So these integrals diverge, and I have to regulate these divergences somehow. And I guess you know that the standard way nowadays of doing it is what's called dimensional regularization, which consists of analytically continuing the dimension from being an integer 4 to something non-integer. And this something non-integer, I just parameterize it by this little quantity epsilon. Yeah, and the 2 in front of the epsilon is conventional. So epsilon is some small deformation away from 4 dimensions. Now, why do we do that? Well, because you can actually show that if after this operation, which is purely mathematical, your integral will be a meromorphic function of the dimension. So I remind you what meromorphic function means, something that you may know from your complex analysis lectures. It's a function with poles. And the poles you can show will be at most at integer values for d, or equivalently at half integer values for epsilon. So if you look at your integrals as arbitrary functions of, well, not arbitrary functions of the dimension, but of arbitrary values for the dimension, you see that this function, this integral will be well defined, except possibly at places where the dimension is an integer, which is precisely what we have. And that is where these integrals diverge. And then you can use complex analysis, and you know that if you have a function that has poles, you can expand it into a Laurent series close to the pole. And so if we work in dimensional regularization, what we usually care about is this Laurent expansion. So this expansion in epsilon. That is what we care about. This expansion starts at some power epsilon to the power k0, where k0 can be positive or negative. And if k0 is negative, For example, if k0 is -1, then the expansion starts with 1 over epsilon. So you have a pole at epsilon equals 0, or equivalently at d equals 4. Okay, so I guess this is something that you know, but I wanted to remind you of it, because what we want to compute is always this long expansion epsilon. Good. So the last thing that I want to mention is the following. It's again, so far I'm doing things that are very obvious. My integral has a well-defined energy dimension. Why is that? Well, when you look at the definition of the integral that we had here, you see, well, every k and every p is momentum. It has a dimension of an energy. So you will get, from the integration measure, you will get d components of the loop momentum. Every propagator will give you 2 energy dimensions in the denominator, raised to the power nu. And I assumed that my n is homogeneous, so that also the numerator has a uniform energy dimension. And so the energy dimension of my integral will be the components of loop momentum per loop from the integration measure. For every propagator, I have to remove 2 energy dimensions in the denominator, and also I have to take into account that I've raised the propagators with arbitrary powers. And of course, there's also the energy dimension of the numerator, n, and I assumed n to be a homogeneous polynomial, so there's essentially the degree of the polynomial, if you want. Okay, so that is something very obvious, but it implies something that is already non-trivial. Well, not difficult, but non-trivial. Because assume that my integral depends on some energy scales S1 to Sk. Right? So S1 could be, I don't know, P1 square, S2 could be P1 or P2, and so on. Now, since I know that my integral must have a certain energy dimension, my integral, which naively is some function of S1 to Sk, must depend on them in a special form, because it must be some energy scale which has precisely this dimension I, and I have to divide by 2 because usually my Si would be P1 squared. They are Lorentz invariants, so they are energy squares. And then the rest must be a function of dimensionless quantities now, so of ratios of scales. So you see that I can already just by some simple dimensional analysis say that my integral has a certain internal structure. So just by dimensional analysis, it must depend on some scale to some power, which I can predict, it's the dimension of the integral, times some function which depends on one variable less. That's the first lesson. So we have already learned something about our integral. But you also see now, so what happens if the integral does not depend on any scale, if it doesn't depend on any energy dimension? Well, and sorry, yeah, if it does no, and if this does not depend on any energy scale, so what could it be? The only thing it could be is that it vanishes. It's actually something non-trivial, but it is true that you can actually prove in dimensional regularization, it's important, that if you have an integral that does not depend on any energy scale, it will automatically vanish. You can think of it as follows. Imagine you have an integral that does not depend on any energy scale, so not on S1 to Sk, not even on S1. Well, I could say, well, but then maybe I can give a mass to propagators, for example. This would be some S1. So then it would be S1 to some power times a constant. And now I send the mass back to 0, and I get 0. That's the idea behind it. Okay. So those are now the 3 things that we can just say in pure thought. So we have defined the integrals. They are Lorentz invariant. They only depend on dot products. They may diverge, so we work in dimensional regularization, and what we care about is the Laurent coefficients. We do not care too much about the functional dependence on epsilon. We care about the Laurent expansion close to d equals 4. And these integrals have a well-defined dimension, and if they do not depend on any energy scale, they vanish. Okay. So far it was just some easy properties. But now we'll kind of use these properties to do a bit more. Are there any questions at this point before we move on?
There's nothing in the chat yet.
Okay. So I guess we can move on. But if you have any questions, just raise your hands, put them on the chat, or just interrupt me. Okay, so let's come to the question of how you can actually compute these objects. Well, to be fair, there's no general solution of how to do it. There are various techniques out there, but very often there's no the winner takes it all strategy. So depending on the integral, one strategy works better than the other. I'm going to read you one of these strategies now, but keep in mind that depending on the problem you want to solve, you may need other strategies. And actually, I think in other SAGEX schools, for example, in Hamburg 2 years ago, so other strategies were also presented. Good. So now let's come to actually computing these integrals. And before we compute them, we can actually ask a much more basic question, namely, which integrals do we need to compute? So why is that an important question? Well, if you take a two-loop amplitude, you just count the number of Feynman diagrams if you want, you may quickly end up in a situation where you may need to have to compute thousands of Feynman integrals. And the question that naturally comes up is, are they all independent? Or would it not be better to find a basis? Because there's no point computing 1,000 different integrals if you realize that in the end that only 10 of them were linearly independent. So how can you possibly find a basis? So that's going to be the first question that we need to answer, or that we want to answer. Given a collection of Feynman integrals that comes out of your computation, how can I find a basis? And the idea goes as follows. So remember that I have defined my integrals as depending on these new i's, these exponents of the propagators. And I'm now going to look at the integrals as being functions of these new i's, functions of these exponents. So each integral now, I will look at it as a function of the exponents. Now, remember that I said these exponents are integers. So naturally now my integral, seen in this way, will be a function on some lattice Zn. So if I fix the values, the integer values for nu1 to nu(n), I will define a point in this lattice. Good. So, okay, that's fine. So now I decide that my integral is actually defined by putting like a point on this lattice. But what does it buy me? Well, the idea is we want to find recursion relations that relate different points on this lattice. And using these recursion relations, we want to find the minimal sets of integrals, or the minimal number of points in this lattice, if you want, that are sufficient to recover all the others via these recursion relations. So that's the goal. How can you find these recursions? And the idea is very simple. So these recursions would be ways of relating different values for these exponents. But you can easily convince yourself, and we'll actually show it now, that shifting an exponent, if you shift nu1 to nu1 plus 1, that is essentially, since they're exponents, the same as differentiation. So let's look at it. Let's look at an example. Imagine you take a propagator, k plus p squared, wherever this thing comes from, that's a propagator, and it's raised to the power nu. If I differentiate with respect to the loop momentum, I get the same propagator raised to the power nu plus 1. But of course, I also produce a numerator and some numerical prefactor that is not so important. So yes, I've shifted the exponent, but of course, I've also not reproduced exactly the same object because I have this numerator, which is actually, well, it's a vector, okay? It is k mu. So, but before we answer that question, what happens to this numerator? The question is, so, well, let's do it. Let's say like this. If I now, it tells me that if I act with the derivative in the integrand on something, if I act on the integrand here, I get back similar objects with shifted exponents and these numerators, but let's forget about them for now. So I get on the right-hand side things with integrals that relate with different values of nu. But in order for this to be useful, I need to say what this is supposed to be equal to. Otherwise, I don't have an equation. Right now, I just said the integral of the derivative gives me back things with different powers for the exponents, but the integral of the derivative is not what I was interested in. So what is this integral of the derivative? And well, I guess you can kind of guess it, because this integral looks very much like the integral of a total derivative. So it would be like the value at the boundary, but my integration domain has no boundary. So naturally, the only thing it can possibly be is 0. And that's indeed what it is. There's actually something we will prove, at least heuristically, that in dimensional regularization, total derivatives for Feynman integrals will always vanish. So that is what underlies this whole idea of finding relations among integrals. That's the main theorem. So let's quickly go through the proof, at least heuristically. The proof actually is based on Lorentz invariance. And let's just look at translational invariance. The other generators work the same way. So clearly my integration measure is Lorentz invariant. My integration domain, well, it's integrated over whole space, is Lorentz invariant. So if I have an integrand that is Lorentz invariant, that tells me that the integral is Lorentz invariant. Let's forget about issues of convergence. I work in dimensional regularization and everything is convergent. So it means that if I shift the momentum k by p, the integral doesn't change. Okay, so that's what translational invariance tells me. So let's assume p is very small, p is infinitesimal. Then, of course, I can expand in P, and I get this thing here, okay? And you see now that actually this term cancels against this term. And you see that to linear order in P, you get that the derivative vanishes. Now, this is a bit heuristic. You can do it more rigorously. But you see that it is the Lorentz invariance, or here the translation invariance of the integral, that tells you that integrals of total derivatives must vanish. You can go through the proof a bit more carefully, a bit more rigorously, but that's essentially the core of it. You can also see it as follows. You know that if you have a symmetry in quantum mechanics, it means that you leave your system invariant. If you go to the Lie algebra, to the generators of the Lie algebra, if you have the symmetry group leaves it invariant, the Lie algebra will kill the object. So that is essentially what's happening here. So you have that this guy, this is the group. The group leaves the object invariant. So the generator of translations, which is the derivative, must kill the object. That is what underlies it in the end. Okay. Good. I don't see any questions, so assume that this is clear. If not, please shout. Okay. So we still have to address this issue of these numerators that we produce from the derivative. Because if I want recursions for shifted propagators, well, if I produce these numerators, I would always produce something new. I would not be able to close the recursion if you want. So how can I deal with them? I can deal with them by writing numerators as inverse propagators. This sounds a bit mysterious, but we will see that in an example now. Let's go back to the example that we, to the example that we had, but now, since everything is Lorentz invariant, I will not just look at ddk mu, but I will contract it with some other momentum to get the Lorentz invariant differential operator. And if I do that, you see I produce the numerator factor now. I get, before I had k mu plus p mu, now I contract with p, so now I get k dot p and p squared. And remember my convention, k's are loop momenta, p's are external momenta. So the p is an external momentum here in my sketchy notation. So the p square is constant, has nothing to do with the integral. So this guy is harmless. This guy is a constant that goes out of the integral and doesn't do anything anymore. The k dot p, however, depends on the loop momentum. So that is something that really sits in the integral. And it's not something that I had on the left-hand side where the numerator was unity. What I can do is I can simply complete the square. Because k dot p is just, well, k plus p squared minus k squared minus p squared. And now all of a sudden you see that the things that appear in the numerator, they all look like propagators, but inverted. So actually what it becomes the following. So the first object, well, the first term, which comes from here, gives me this, where the only thing that has happened is that the nu plus 1 that I had here has become a nu again. Okay, because I've cancelled k plus p squared. Then the rest, which is all of this, becomes this. And of course, now the exponent in the denominator, nu plus 1, stays nu plus 1. So nu plus 1 here remains nu plus 1. But now this numerator, I can interpret it in the following way. It has this p squared term, which we said is harmless, because that's a constant, has nothing to do with the integral. While the other term here looks like a propagator, but in the numerator. So that would be, so this term here is like 1 over k squared to the power minus 1. So that is like another propagator raised to the power minus 1. So here it would be something where the nu of that propagator is minus 1. Okay, so here you see how important it is that I allow for really these arbitrary powers of the propagators, including negative powers of the propagators, which means that these things sit in the numerator. Is that clear? If not, please shout. Now, one caveat, well, you see it from the discussion here, the k square was not originally there. So this thing, this propagator, 1 over k square, was not in my original expression. Okay, so the fact that I can write all numerator terms back in terms of propagators, possibly propagators raised to negative powers, is not always possible by construction. I always need to start from a set of propagators that has, if you want, a certain closure property, that has the property that it does not, you don't produce new things when you write numerators back in terms of propagators. And this is something that's possibly Ben or Young would also comment on, something that's sometimes called irreducible scalar products in that context. So you should not have these irreducible scalar products. So before we go on, let's formalize this with some vocabulary, because this is something that if you read papers on loop computations, you often have this vocabulary that is comes from these what's called integration by parts relations. So integration by parts relations we just discussed, IBP relations. This is the idea that integrals of total derivatives vanish. It's called integration by parts because it's really like integration by parts, except that the boundary term is 0. So we have said now that these IBP relations, they define recursions on the lattice. And this lattice defined by the values of the exponent. A word that is often used in this context is something that you call, is called a topology. So what is a topology? A topology is, if you want, the graph that you started from. So it's a set of propagators that define your family of integrals. Family in the sense of integrals that just, so the family is defined by the values of the nus, of the exponents. So two integrals belong to the same family if they correspond just to different values of the nus, but the same set of propagators. But I also require something more. I require that every scalar product between loop momenta and or loop momentum and external momentum, I can write it as a linear combination of inverse propagators. Maybe I should have said here inverse. Okay, that is this operation that we've done here on this slide, but it's shown in red here, that every dot product is a linear combination of inverse propagators. Here k plus p squared, k squared, and p squared is constant, that has nothing to do with the loop momentum. Okay. Another word that is often, that you often see when you read about these IBP relations, is this concept of a sector. A sector in this IBP language is simply the region on this lattice where these exponents have a definite sign. For example, where nu1 is positive, nu2 is negative. That would be a sector. And depending on the literature, sometimes, so positive, negative, and also zero are maybe distinguished. It depends on the literature. So when you hear the Mathematica codes that we'll see later talk about sectors, or you see in the literature say, in this sector, there's the recursions do not give anything, there's no master integral. We'll see what it is in a second. It just means that you grouped your lattice into regions where these exponents are positive or negative. Why is that a good idea? Well, remember that the news being positive means that the propagators are raised to a positive power. So they are really denominators. So the propagator is there. While if the exponent is 0 or negative, it means that this term is either absent or in the exponent. So the propagator is not there. So you see, for example, here, we said that here nu is -1. So that would be in a sector where the exponent of this propagator is negative, which also means that the k-square propagator is absent because that term sits in the numerator. We will see that in an example in a second. As a concept, it's not very difficult. It's just you partition the lattice into the regions where the exponents are positive in it, or possibly 0. And so once you have this lattice, you have the IBP relations. You can try to solve the recursion. And you can actually prove, it's a theorem, that there's always a finite dimensional solution space. So the recursions will always be linear because they come from integration by parts. Differentiation is a linear operation. The recursions will be linear. If you solve them, you will get a vector space of solutions, and this vector space always has a finite dimensional basis. And so that you will never get to a situation where you have an infinite number of master integrals. It will always be a finite number. And the basis is often called master integrals. Now, I insist here that master integrals are just a choice of basis for the solution space. There's nothing intrinsic to being a master integral. There's not that if integral 1 is a master integral, integral 2 is not. So it's not that integral 1 is better than integral 2. It just means when you read the paper that when you say the master integral is this and this, it just means that I made a choice of basis which consists of this and this. It does not mean that master integral is anything mysterious or better. What you call master integrals is just your choice of basis. It's a choice of basis for a vector space. You could have made another choice. Okay. I insist on that because often you read in papers a bit in a sloppy way that people say, this integral is a master integral, this other integral is not. It's not true that you can be a master integral or not be a master integral. It's just that you make a choice of basis, and either you are a basis element or you're not a basis element. But one basis is as good as any other, at least at this stage. Then when it comes to actually evaluating the integrals, because now we will have to evaluate the basis integrals, the master integrals, of course, then some integrals may be easier to evaluate than others. That's a different story. Okay. Questions before we move on to some example? No?
Hi, Claude. I would like to ask, it's not clear to me how we get rid of the extra propagator. So when we use the IBP, we generate some term of denominator that we can rewrite as an inverse propagator.
Yeah.
So the number of propagator is infinite when we consider this space of functions.
What do you mean infinite?
In the sense that the number of propagators grows in some sense. We generate this k to different power to the denominator with the IBP. So I don't see really how the relation close, the recursion relation close. It seems that we generate something new.
So maybe let's wait 2 minutes because then we see an example. So maybe then it's clearer.
Okay, yeah.
And if it's not clear, we can go back to it, okay?
Okay.
So maybe let's look at an example. So maybe that makes it better. Yeah, so let's first look at an example and then we go back to this comment. So let's look at the example of the massless one-group bubble. So it's a very simple example, and it shows it because you can really do everything by hand and see every single step. So I will look at this bubble integral. So sorry, I look at the family, which has two propagators. So it's, you see the Feynman diagram here. It has two propagators, k squared and k plus p squared. P is the external momentum. And each member of this family is defined by these two integers, u1 and u2, which are these exponents. Okay. And not by chance, I also chose the example such that it matches the example of the derivatives that we computed before, because then you can easily see the connection now. So what can I say about it? Well, the first thing, I guess, you see it from the graph. The graph has an obvious symmetry. Namely, if I swap u1 and u2, the integral doesn't change. So that's clear. So then let's look at the IBPs. Well, yeah. So let's first go, to answer your question, we go back to these slides in a second. So the IBPs would tell me that if I take the integral of a total derivative, I get 0. And the derivative of what? Well, my integrand, which are my two propagators, raised to the powers u1 and u2. But I also include some other vector because dk mu is a vector, but I want a Lorentz scalar. So what other vector could I choose? Well, I only have two choices. It's k or p, because that's the only vectors that I have in my game. Right? If I want this thing to close, it can only be k or p. So if I now go and I evaluate this derivative, you can easily do it. I just show you the result, but it's a one-line thing. You get the following. So you get for, maybe I should have said that. The first line is v equals k. The second line is v equals p. So what you get is, in the first case, well, you get always back an integral from this family, but with possibly shifted values for the news. So if I start with a fixed value, integer value for u1 and u2, I will just produce 3 terms with derivative. If I, for v equals k, I produce 5 in the other case, and v is equal to p. I don't produce an infinite number. What will happen? Well, what will happen is that if you, well, if you want, we can also go through the calculation. It's not too difficult. Let's maybe take this guy. So what would happen? Let's say v is equal to k. What do I get? Well, I get, if I do the derivative, I get dk mu k mu. I get, that gives me d. And nothing else. So that gives me bump u1, u2. Then I get a contribution from k mu, and the derivative now acts on the first propagator. And the second one is outside. And I get a term where the derivative acts on the third term. Good. And so now what you see is that this thing, what is it? Well, that is minus 2 nu 1 k mu over k squared nu plus 1. But you also have this guy here, so that you actually cancel the plus 1. Okay? And for this term, you get, this is actually what you had in the previous slide. You get this k mu plus p mu over k plus p squared mu 2 plus 1. And then you have to go back to when you contract with k mu, so that then this becomes two k dot p plus 2p squared. Now you do what we did 2 slides ago. I take this and I complete the square. So this we had in the previous slide, or 2 slides ago, minus k squared plus p squared at minus p squared plus 2p squared. And so you see you get one term where you kill this, and another term where you get you have one new one, and here you have k squared in the numerator, so that gives you an overall k squared nu 1 minus 1. So you get 2 terms. So you get, so what do you get? You have the term with d, which is this guy here. You have a term where you have shifted, well, yeah, this also gives you nu 1. So it's nu 1. It remains the same. You have a term where you have shifted nu 1 to be less than 1, which is here, and you have increased nu 2. And you have a term where you have increased nu 2 alone, which is, which comes from the p squared term here. So those are all the terms that you produce. You do not produce an infinite number of terms. It was enough that I can write k dot p and complete the square, and complete the square in such a way that it is only inverse propagators. Does it answer your question?
Yeah, absolutely. I was not thinking about v equal to k. I was thinking about v equal to p. So I was not understanding, you know, how to close the things. But you have, if you have both, you generate much more relations.
You could choose any vector v. Of course, in practice, you choose those independent vectors that you have in the game, meaning loop momentum and external momentum.
Yeah, thank you.
Okay, so those are the IVPs. But let's go a bit back because it jumped over to a couple of things. Namely, so there was this notion of sectors. And one thing that I want to mention is what is shown in green here. It's an important thing. Sometimes summarized, the scaleless sectors vanish. What does it mean? Remember, we said at the beginning, if you have an integral which does not depend on any energy scale, this integral must be 0. But now imagine that I have no propagators at all. which means that my news are all, sorry, this should all be negative. I apologize. This is a mistake. The news should be, if the news are all negative, sorry. If the news are all negative, then all the propagators are inverted. So I just have this polynomial in the numerator. But if I have a polynomial, if I have something like, let's take an example. Imagine I have just polynomial, something like this. K dot P. But the P has nothing to do with the integral, so I can pull it out. So what I get is an integral which does not depend on anything and no energy scale. The energy scale, I've taken it out. The integral does not depend on an energy scale anymore. So this integral must be 0. And you can easily convince yourself that this will always be the case. As soon as you have an integral without propagators, which means that the news are all negative or 0, this integral must be 0. This will be very important. This also means that there are certain sectors, namely the sectors where all the exponents are negative or 0. These sectors you can just throw away. They have no information. They're all just trivially 0. Okay. So let's go back to our example, this bubble integral. And so what are the sectors? Well, the sectors are the regions where nu1 and nu2 are positive, negative, or 0. So I list them here. Okay, so they're just listed according to nu1 positive, nu2 positive, and so on. So which of these sectors are 0? Well, we said that all those that do not have any propagator or do not depend on energy scale, in particular those that do not have a propagator, will automatically vanish. So let's check it. First of all, if all the news are negative or 0, the integral vanishes, the scalars. So that happens precisely here, right? So those guys would have all the news negative or 0, so the integral vanishes. On top of that, you see that if this exponent here is 0, then there's no dependence on P, so there's no dependence on any energy scale, then the integral also vanishes. And that nu2 being 0, that is this region here. So also those integrals must all vanish. But there's actually more, because now you can say, well, but actually, if nu2 is negative, then my energy scale only appears in the numerator, and then I can use the argument from before and just pull it out. So also, this sector where nu2 is negative will be 0, because, for example, if nu2 is -1, then k plus p squared is in the numerator. I can expand it out, and I get this equation shown here. But we said that 0, 0 vanishes. 1, 0 would be here. That also vanishes. And the last guy is 0 by itself, because it does not depend on any energy scale. So also, this element up here must be 0. And by symmetry, we said that I can exchange u1 and u2. It means that also, if this is 0, this is 0. If this is 0, this is 0. So you see that all sectors are 0 except this sector plus plus, where both propagators are present. So that's already one important lesson that I've learned, is that of this infinite family of integrals, which were parameterized by integer values nu1 and nu2, The only ones that I actually care about are those when u1 and u2 are both strictly positive. In all other cases, the integral is just 0.
Sorry to interrupt. David has a question.
Yes, I have a question. If you have a mass, the things change a bit, right?
Yes.
If you have a sector which is 0, if you have a mass, it is possible that it is not 0.
Of course. I was discussing here this integral here, which the propagators don't have a mass.
Okay.
But this discussion is for this particular example. Okay. Now, however, what would change is that if you have a mass, then, for example, this sector would be non-zero, because now you would have, so this is 0 because the integral in there looks like this. It has no energy scale. However, if you have a mass, it would have an energy scale, which is the mass. And then this sector would be non-zero. Okay, yeah, thanks for the comment. Okay. So for this example, so the analysis of the sectors, you have to do it case by case. More questions, more comments? No? So you already looked at the IBPs, and let's rearrange them a little bit, and then they become this. And so what have I done here? Well, here I've effectively solved the recursion. So what does it mean? So let's look at these equations a bit. So these equations tell me now that if you take any integral in my family for arbitrary values of u1 and u2, I can always write it as a linear combination of two other integrals, namely, where a linear combination of two integrals where one of the two exponents has been lowered. So where either I have lowered nu2 or nu1. And the same here. So I can always replace an integral by a sum of two integrals where one of the two exponents has been lowered. There's one caveat, which is that you have these denominators here. So that is why you really need these two relations, because if you're kind of in the bulk where both values for u1 and u2 are both greater than 1, then you could use either of them. But as soon as you get to kind of a boundary, we will see in which sense this is a boundary in a second, where say nu1 is equal to 1, then you could still use this relation, but you could not use the other if nu1 is equal to 1. Good. So let's look at it. So here you see the lattice. This is the plane for u1 and u2, and the dots are the points of the lattice. Each dot indicates an integral for that value of u1 and u2. Good. Now the first thing I know is that my integral that I have all these scalar sectors. I need at least both values, u1 and u2, to be strictly positive, otherwise the integral is 0. So first thing I can do is I can throw out all the points where one of the 2 points is negative or 0. The integral is scalar, it vanishes. So I only care about the first quadrant. The other thing I know is that the integral is symmetric in u1 and u2. So I can draw this diagonal, and I can always replace integrals where u2 is greater than u1 by an integral where u1 is greater than u2. Good. So let's assume you have this integral which corresponds to nu1 equals 7, nu2 equals 4. Now, what we said is I can use the IBPs and replace this integral by a sum of two terms where one of the two indices is lower. So I can replace this integral by sum of two integrals, which correspond to 6,4 or 7,3. Good. So now I have a sum of two integrals to compute. So you can say, okay, that's not, doesn't buy me anything. Now I have to compute two integrals instead of one, but I can keep going. I can replace each of the two integrals by a sum of two other integrals. So two of them coincide, so I get sum of three integrals. And I keep going. So now I get four integrals. Now I get 5, but actually, I guess you can easily see that because of symmetry, this integral must be the same as this. So I can now flip it over and I just get back 3 integrals. And I keep going. Now, well, already actually before, already here in this step, there was a caveat. So you see here, this point here was 7,1. And remember in the recursion, there was this problem with 1. But it actually, if you carefully, it turns out that that just means you use one of the two relations, which means you only move horizontally. The other one would end up here and it vanishes. So you keep going. You just keep going. Whenever you get nu2 greater than nu1, you flip it over. You keep going, until you get to this situation, where now you see you ended up at the point 1, 1. So actually, what you've obtained now is that your integral 7, 4 is actually equal, proportional rather, to this integral 1, 1 down here. And we can say, well, keep going. No, you can't, because remember that my recursion had this problem when one of the two nus is equal to 1. I could not use one of the two relations. Now both exponents are equal to 1, so I cannot use any relation. So here I have to stop. And so what I've obtained is that my integral 7, 4 is actually proportional to the integral 1, 1. And so I would call this integral a master integral. It's actually what I've shown is that at whatever point you start from on this lattice, so either the integral vanishes, it's a scaleless integral, or you're in the first quadrant, but then this integral is proportional to this point, to integral that sits at the point 1, 1, which is then the basis for my space of integrals. And I call that basis, well, in this case, it's a one-dimensional basis, and I call the element of that basis a master integral. Okay, are there questions?
I have a question about the two relations.
Yeah.
So when you're at an arbitrary point, not near where none of the nus is 1, you can use both, right?
Yeah.
So does that give you extra relation between integrals, the fact that you have two relation with different coefficients?
I would need to think about it carefully, but my answer would be no, because I know that that is the solution of the recursion. So that is the minimal number of relations that you have.
Okay.
Not the maximum one. There are no other relations. At least no other known relations. Of course, I cannot prove mathematically that there are no relations, but those that come from IBPs are those.
Sure.
So every other relation would be a consequence of these two relations. You can, of course, go and put them equal. You get a third relation which tells you that this is equal to that. But that is just a consequence of the two relations that I wrote down here.
Okay, yeah. And it's a general feature of IBPs that you get many such relations, I guess, or?
Well, let's in practice, what I described now is not how you solve them, because in practice, solving these recursions is super complicated. The bubble integral is simple enough that you can actually do it. And I thought it would be good to show it because it shows you what IBP relations are and how they work. Now, how you do that when you have an integral with 12 propagators is a different story. Okay.
All right, thanks.
So Good. So conclusion, there's one single master integral, which is this bubble integral with two propagators raised to unit power. You can easily Feynman parameterize it, and you get that this integral is this simple expression shown here. I'm not going to dwell on it. I just show it because we will use it in tomorrow's lecture. But this is something you've seen in your quantum field theory lecture. It's easy to compute. Now, actually related to the question right now and also my answer. So here I've shown you really the recursions and how to we've solved the recursion for the bubble integral. But now imagine you have a complicated integral with 12 propagators. Finding the path in this 12-dimensional lattice with many different identities and recursion relations and how to solve the recursion relations is super hard. And I'm not saying it cannot be done, but it's super complicated. Therefore, in practice, one uses some other strategy. And the strategy is as follows. So your IBP relations are linear. By construction, they're always linear, they're linear relations. So just kind of sample identities where you plug in values for nu1, nu2, nu3, integer values. You plug in integer values. And of course, well, in principle, you would need to sample this infinite dimensional lattice, but cut off when the sum of these exponents, actually the sum of the absolute values, is less than a certain maximal value. If you cut them off, you get a finite-sized, very large, but finite-sized linear system, which you can solve by Gauss elimination, for example. So why cutting off the system is something you can do? Well, because you know that in your calculation, you won't care about the integral with exponents 25, 27 for your bubble. You care about the integral with exponents 1, 1, 2, 1. So cutting off at some high value new marks will be good enough. And so in this way, you can reduce it to solving a linear system. And this procedure has been implemented in various Mathematica codes or C++ codes. And we'll look at one such code in a second. And we look at it on the example of the massless box. I just show you here the definition. Set has 4 propagators. And it depends on these Mandelstam invariants S, T, and U, the standard objects, and the sum of them is equal to 0. Okay. And we will now look at the IBPs that you get from a code called LightRed. That's the last thing for today's lecture. Can you see my Mathematica screen?
Yes.
Good. So let's so you can download this code LightRed. It's publicly available. The reference is in the lecture notes. I will make the slides available later.
Claude, could you increase the font size a little?
I'll try. I'm close to maximum already. That's the maximum now.
Thank you.
So I've just loaded the code. Now the first thing is that you have to define all the quantities. So you have to read the manual to see the details, but first thing is I have to define which symbol I use to denote the space-time dimension. I have to define which quantities are vectors, which quantities are Lorentz scalars. So K will be my loop momentum, P1, P2, P3 are my external momenta, they are vectors. And S and T are numbers. There's also the Mandelstam invariant U, which however is minus S minus T, so I don't need it. And I also don't need P4 because the momentum conservation P4 is minus P1 minus P2 minus P3. And I also have to define all my dot products between external momenta. P1 square is 0, P2 square is 0, P3 square is 0. P1 or P2 is S divided by 2, because S is 2 times P1 to P2, P2 to P3 is T, P1 to P3 is U, which is minus S minus T. I have to define my propagators. The propagators are K plus P1, K plus P1 plus P2, K plus P1 plus P2 plus P3. And I have to tell the code that the loop momentum is K, the others are external momentum. So now I just define, well, this is just the name that I give to label my integral family. I call it massless. You could call it massless box as a material. Props is my list of propagators. Loops is the list of loop momenta. I want the code to generate the IBPs. I want it to analyze the sectors, to find 0 sectors, and I want to find the symmetries. A comment in light red notation, the sectors are such that if it tells you, so the sectors will always be sequences of zeros and ones here. One meaning that the nu is positive in that sector, 0, the nu is negative or 0. For example, the sector 1010 will be, will mean that nu1 is positive because I have a 1. Nu2 is negative or 0 because I have a 0. Nu3 is positive, Nu4 is positive. And so if I run this, it should actually hopefully do it. Let me start again. Maybe I missed some execution. Now it runs. Perfect. So here it's now, this is the output. It just says found 9 0 sectors. Okay. For example, you can actually, it shows you here, you have to read the manual, but it shows you what are kind of the outputs that you can access now. For example, if your IBP of my family they're called massless would be the IBP relations. It can tell you which sectors are 0 sectors, non-zero sectors, and so on. For example, this would be the IBP relations. The language is a bit cryptic because it's internal, but this would be nu1, nu2, nu3, nu4. J is always the integral. This is J is the integral with values of nu1, nu2, nu3, nu4, and the hashes are just because they're placeholders. And this would be the relations, the recursion relations that relate them to different values of nu1. It can tell you which sectors are 0 sectors. For example, when all the propagators are raised to negative powers, then the integral is scalars. It vanishes. But there are others, and I invite you to check that all these are indeed scalar sectors. So now that I have the IBPs, I can ask the code to solve them. Again, you need to look at the manual to see the syntax, but now it goes through every sector that is non-zero, and it solves the recursions in there. And it tells you if it found a new master integral in the sector. For example, in the sector 0101, it found one master, which is the integral with nu1 equals 0, nu2 equals 1, nu3 equals 0, nu4 equals 1, and so on. This sector, it found one master, this sector, and so on. And so after it finished running, you can ask it, so what are the master integrals? These are the master integrals. There are 3 of them. So one has in nu1 equals 0, nu2 equals 1, nu3 equals 0, nu4 equals 1. So it has 2 propagators. It's a bubble. This one has 2 other propagators. It also has a bubble. And this one has all 4 propagators raised to power 1. So that is the box. Now, once you have them, you can write every other integral. For example, nu1 equals 2, nu2 equals 3, nu3 equals 1, nu4 equals 1. You can IBP reduce it to a linear combination of these 3. So this is an identity among integrals. It tells you that the integral with the powers of the propagators being 2, 3, 1, 1 is this linear combination of my 3 master integrals, which are the integrals 1, 1, 1, 1, which is the box, which is down here. and the two bubbles that are shown here. Okay, good. So I think this is all I wanted to say today, because after that we will now continue the lecture and discuss tomorrow how we can actually evaluate now these three master integrals. So I think this is a natural place to stop. So if you have any questions, now is a good place to ask. Otherwise, you can also ask tomorrow morning. Thank you.
Robert, would you like to unmute yourself?
Hi. Do you always consider integral expressions where your integrand has no numerator? Do you always massage your integral such that you either pull out factors from your numerator or write factors in your numerator as propagators?
Yeah, that is, yes. So you always write them as inverse propagators. So you have numerators. Whenever you have a nu that is negative, it means that this term is in the numerator. So they are there. They are just written as inverse propagators.
Okay, cool. Thank you.
And we'll then continue tomorrow and discuss how we can actually evaluate these three master integrals.